So as we saw in the last segment, a binary search tree by itself can become unbalanced if you're unlucky with the sequence of insertions you do into it. And we have to ask ourselves how we could keep it balanced. So we need a way of modifying these trees so that if we see them getting lopsided, we do the bookkeeping to keep the balance and keep the height at around log n instead of around n. So we need to modify the trees while preserving the search tree property that the key at a node is greater than the keys in the left subtree and less than the keys in the right subtree. So we need to preserve that. So one operation that helps to preserve these operations, this property, but still helps balance the tree, is an operation called rotation. So what's rotation? I'll show it to you by a picture. And it's a schematic picture, but imagine you have a binary search tree with a key x at the topmost node that you can see. There could be more of the tree above this, but I'm not going to show that. But in fact, this tree could continue above here. And the same tree this tree could also continue above here. So x is some node in the middle of the tree, and x is some key in the middle of the tree. It has a left child with key y. What do we know from that? Because of the search tree property, we know that y is less than x. And then y has a left subtree called t1 and a right subtree called t2. X has a right subtree called t3. And here is a way you can make a right rotation on the tree. So you can sort of think of it as something that's happening like this. So it's kind of rotating y and x and see what happens. So we move y to take the place of x. But of course, x has a key that's greater. X is a key that's greater than y. So we need to make x the right child of y. That's the kind of rotation that's going on. And now what do we do with the subtrees? What do we know about the subtrees? We know that the keys in T1 are all less than y, which are less than x. So clearly T1 should be put on the left child of y, in the left subtree of y, as the left subtree of y. Now the keys in T2 are greater than y, but less than x. So they should be in the right subtree of y, but in the left subtree of x. So this is exactly where they belong, the keys in T2. So we can hang T2 here. And the keys in T3 are greater than both x and y. And so we can make them in the right subtree of x and y. So that's T3 here. So you can see intuitively, and you can prove this formally if you like, that this rotation operation preserves the binary search tree property. Now, a judicious use of rotations can be used to balance the tree at all stages so that the tree never gets very lopsided. And in particular, there's one kind of balanced binary search tree called the AVL tree, where what we do is after we insert or delete an element, we always maintain the property that for any node, the left subtree and right subtrees have heights that differ by at most 1. So we do whatever rotations are needed to ensure this property. We can do this efficiently, and if we do this all the time, we will get order log n. So we've seen that binary search trees are one way to implement the dictionary data structure. They are fast, they work in log n time if you can keep them balanced. But the code for binary search trees is a little complicated, especially if you want to keep them balanced. A much simpler way of implementing a dictionary is hashing. So what's the idea of hashing? We actually implement the dictionary using an array, but then you have to take the universe of all possible values you might want to store into the dictionary and map them into the array somehow. And the mapping is done by something called the hash function, and the image of the hash function is called a hash table. So just as an example, suppose all the possible elements you may ever see in the dictionary are all the integers. You could define a hash function that maps any element of the universe x to x mod 37, let's say. What does x mod 37 mean? It's the remainder when you divide x by 37. So what are all the possible values that x mod 37 can take? Well, it can be 0, 1, 2, 3, all the way up to 36. We know that the remainder will never be more than 37, so it's 0 to 36. So imagine you have an array with indices 0 through 36. Now if you take any x from the universe, you just map it to that location in the array which is x mod 36, for example, 37. So for example, if x is 50, you would map it to 50 mod 37, which is 13. So it would map to the location 13 in the array. Okay, so that's the hash function. Now, if every element in the universe maps to a different location in the hash table, then insert, delete, and find are all very easy order 1 operations. To insert an element x, you just map x to x mod 37 and store the record containing x in that location. To delete an element x, you look for x in the location x mod 37, and when you find it, you take it away, you remove it. So that's also order 1. And to find an element x, it's the same thing. You look for x in the location x mod 37. That's just one example of a hash function, mod 37, but you could have other functions that, for example, use mod other values depending on how many elements you're going to store, or there are even more sophisticated hash functions than these, just not pure mods. But now suppose we have m different keys and a hash table of size n. This is a random process. Imagine that the keys are coming at random, and suppose we were actually mapping not to x mod 37 but to a random location in the array. What do you expect to have happen? The probability that any one key maps to any one location is going to be 1 over n. Because we're mapping it to a random location, there are n locations. All locations are equally likely. So there's a 1 over n chance that a key will land in some particular location. So probability h of k, the hash value of k equal to some location I, is 1 over n. So let xi be the number of keys that are mapped to location I or index I in the hash array. Then the expectation of xi, that is the expected number of keys that will land in location I, recall linearity of expectation, is the summation over all keys of the probability that key maps to location I times 1. So if that key, so what we're doing really here is that we are defining indicator random variables which are 1 for each key, which are 1 if that key lands in location I and 0 if they land somewhere else. And then we are summing the expected value of each indicator random variable to get the number of keys that hash to location I. Now for any particular key, the indicator random variable indicating whether it lands in location I has expectation equal to the probability that that key hashes to location I. We've seen this before for indicator random variables. And so that's that expression. And when it does, that indicator random variable has value 1. So that's what this expression says. Now we already argued that the probability that any one key lands in location I is 1 over n. And now summing over all the keys, there are m of them by assumption, there are m different keys. So the total probability, the total expectation xi is m over n. And this is called the load factor of the hash table, which is alpha. Basically, the load factor says how much is each location loaded. Compared to the size of the array, what's the number of keys we're storing there? That's the load factor. Now, all this is assuming an ideal world where every key hashes to a different index. And when that happens, hash tables are really great. The problem with hash tables is that sometimes keys won't hash to the same location. So it might be that we are picking 2 elements in the universe. For example, if you're using the mod 37 hash function, suppose we are hashing the elements 50 and let's say 124. You can verify that both of these map to mod 37. They both map to location 13. So this means that suppose someone inserts the key x equals 50, we'll store it in location 13. Later on, someone inserts x equals 124 into the hash table, and we will try to store it into location 13, but we'll find that location 13 is already occupied. So what do we do then? Well, there's a couple of different options for how to handle these so-called collisions when 2 keys hash to the same value, same index in the array. So one approach is something called chaining, which is pretty much illustrated in this picture here. So instead of storing each item directly in the array, we store a linked list of all the items that map to that index. So for example, if you look at this index here, the first index in the array, index 0, this is showing that there are 2 elements, this one and this one, that both hash to that index, and they're just stored in a linked list. So we could do that. And of course, now when we're looking to insert an element, we would have to go walk down this linked list and insert it at the end perhaps, or insert it at the beginning. Both are possible. If you want to delete or find an element, in the worst case, you may have to enter the array, the hash table here in this location, say it hashes to this location, and then traverse the entire linked list before you find the element. So in the worst case, the time to find and delete could be proportional to the length of the longest linked list in this array. So the runtime of all operations is not proportional to the length of the linked list at the index we're operating on. Now, in expectation, the number of elements that hash to one location is the load factor alpha. So we expect the linked list to be about alpha long. So find and delete should take order alpha time, and inserts too should take order alpha time if you insert at the end. So the worst case can be really bad here. That is that if all the elements, if you really get unlucky, and all the elements that you're hashing hash to the same location in the hash table, then that linked list will be of length m, the number of elements. And then finding an element or deleting an element will take order m time. So hash tables are good in terms of average case or expected performance, but they can be bad in the worst case. So another way of handling collisions is not to use linked lists, but to use something called open addressing. So you want to insert an element x into the hash table. You look at location h of x, and you find that it's already occupied. Then what do? One way of doing open addressing, and there are many ways of doing this, one way of doing open addressing is something called double hashing, where we have a second hash function called g of x, and when we're trying to insert x and h of x is occupied, we look to try to insert x successively in h of x plus g of x. If that's unoccupied, we'll put x there. If that's also occupied, then we'll go to h of x plus 2g of x, and so on, until we find an unoccupied location, and that's where we will put x. So the nice thing about this is that unlike the linked list solution, this requires no extra storage. One hash table is enough, and we don't have to deal with pointers. Everything is in the table. So it's basically array access, which is a little bit faster than using pointers. The negative side of this is that deletion is tricky. So for example, if some element y had been residing at this location, and when we inserted x, and that's why we went and put x over here, because h of x was occupied, h of x plus g of x was occupied by y, and so we put it x at h of x plus 2g of x. Now later on, if someone deletes y, then this location becomes empty. And now suppose we are finding x. We go look for x at h of x. We don't find it there, but we find some other element there, and we say, okay, we should look for x at h of x plus g of x. So we go there, and we find that that location is empty. Does that mean we stop looking for x, or do we continue to h of x plus 2g of x and so on? That's the challenge with deletions, because if we stop, we're making a mistake. X is sitting here. If we don't stop, how far do we go? The h of x plus g of x, 2g of x, and so on can wrap around the entire array, and we may end up searching the entire array. So that is also bad. So there are ways of handling deletions, but they're more complicated with open addressing. So chaining is probably the easier hash table solution. The summary is that hash tables work great in expectation if you don't get a big load factor and you use a good hash function. But in the worst case, they can have really bad performance. As a compromise, balanced binary search trees work perfectly in the worst case. I mean, not as well as hash tables, but they give you order log n performance in the worst case, no matter what keys you're inserting and deleting. So it's a question of whether you want absolute guarantees, or are you happy with generally good performance, whether you use balanced binary search trees or hash tables.